Okay, so for this lecture, we're going to have to talk about two ideas, abstract classes and interfaces. We're doing this order. And this will be just a slight extension to what we learned from the inheritance. So that'll be a nice review lecture for static type, dynamic binding, substitution, etc. So we're going to review that quickly. The way I'm going to do these two concepts will be by doing example, two different problems to solve. Okay, let's do one by one. Let's start with abstract classes. Okay, I'll talk about at the end about which one you should choose to use in general. We'll do that a little bit later. Okay, let's consider this problem over here. Let's go over the problem together and then tell me how you think quickly. Let's say we want to solve the problem for polygons. You all know what a polygon is, right? A shape with more than 3 or more sides, basically. Okay, it can either be a, let's say, triangle or rectangle, either two kinds, right? And then given the polygon, we may want to say, we want to grow its shape by certain units. For example, let's say this. Conceptually, this is what we have, okay? Let's have a quick look. Let's say if I have a polygon like this, if I say this dot grow, okay, what that would do is it's going to just have a larger rectangle, conceptually, right? Okay, just to make sure. Okay, and then compute and return its parameter and also return its area. Okay, so now, here's a question for you. Okay, given that we have learned about inheritance, it wouldn't be so surprising if you simply come up with a superclass called polygon, and then two subclasses. One is called rectangle, the other one is called triangle. Always good. Okay, let me discuss this a little bit with you, and then we go into the actual solution using abstract classes. Let's say, for example, we have a class over here called Polygon, under which we have two subclasses over here. And one is called Rectangle, the other one is called Triangle. Okay? And let's see the problem we want to solve. First of all, we have to somehow store the array of sides for the polygon, right? So now, for that one, I can suggest something very straightforward to you. Let's say we simply got integer array, and then it's simply called sides over here. It's a little bit like an array of courses or array of students. All is good. And now I want to draw your attention to the following methods. About getting the parameter, which means more about the summation of all the sides, right? And also to calculate area. Would you believe where should we define these two methods? One is called get area. The other one is called get parameter. Where should we put these two methods? Where should we implement them? Oh, go ahead first. Implementation. For example, you might just run a simple loop to actually add up all the sides, right? That one tends to be universal for all the polygons. Either it's triangle or rectangle. That's good. Okay, let's go with the second suggestion you're doing, okay? So now for get parameter, that one is kind of straightforward because you can have a general formula for any polygon. Okay? Let's say for the get area. So what you're suggesting is like this. I will put get area over here. Okay? And I will put get area over here as well. So that means I have two versions, right? Am I understanding you correctly that we don't have any get area in the polygon? Well, if you put it there, you better do something, right? No, make a decision, please. Huh? Okay, let's say I like that option there because that's the point I want to illustrate. So guys, let's make the following design. Okay, let's say in the polygon class we don't have get area simply because at this level we don't know how to calculate area in general, and then we got get area here. What would be the problem over here? Let me give you a little bit hints. You can tell me. Think about if we define a variable of static type polygon. Are we able to call get area on that particular variable? Okay, let me make my question more explicit. Okay, so that will be related to your inheritance lecture study. Okay, so let's talk about this particular design over here, and then I'll write a code over here. If I have polygon over here, I will say P is assigned to new, let's say rectangle. I know that dynamically, this dynamic type rectangle is able to support get area. I know that very well. However, am I able to say the following? Let's say system.out.println, and then I would say p dot get area. Would this work? So why would it not work? Because somehow the static type for P over here, first of all, this would not even compile, okay? Because if you look at that, P, the static type over here is simply just Polygon. Well, as you can see, decoration over here. And the Polygon, as we said, does not define the area. It's only defined at the subclasses level. So this will not even compile. So this design is not what we want. Are we okay with this? Okay. And what you suggested as another alternative is to say we might define the area over here, and then we simply leave it just empty. I would say usually when you leave the implementation empty, it's not very useful. That means you just do nothing. Okay. So the idea about abstract class is to say we can somehow define something, for example, get area in the superclass over there, and then we're going to make the implementation so-called abstract, which means at this point we simply don't know how to implement get area. But statically, it should be supported for get area for Polygon. We can rely on the dynamic type for Descendants to implement the get area. That's the whole idea. Okay? Guys, let me summarize, and then we go into the code details. How can abstract classes be useful? Abstract classes can be useful when you have in the superclass methods. It can be one, it can be more. You have the methods over there, for example, in Polygon, that you simply don't know how to implement at this moment because the area for rectangle depends on width multiplied by height, right? And also triangle may depend on other formula. You simply don't know how to implement that universally at the Polygon level. So what you will do is, you will see, we have to learn about a new keyword called abstract. Okay, let me mention very quickly. So what you will do in the Polygon level is you're going to define something called abstract. Okay, it's a keyword that we're going to see. So you're going to say abstract, and then maybe you'll say double, return type, and then get area. And take no input, and semicolon. That's it. Okay? So what that means is the static type of Polygon can now support get area, no problem. And dynamically, either rectangle or triangle is guaranteed to support this method get area. That's what we will see in the code details. Okay? Any question conceptually before we get to the actual code? Okay, let's do it. Okay. Okay, let's have a quick look. Okay, for rectangle, you can simply do length multiplied by width. Have you heard about Heron's formula? I'm just curious. Have you heard about it? It's actually interesting. I looked it up in Wikipedia. So it's a general formula for any triangle. For given any triangle, you can simply, first of all, calculate half of its parameter, called S. And then you simply say S multiplied by S minus A, S minus B, S minus C, and take the square root. And that'll give you the area. Anyway, you can take the formula for granted. Okay? And the point about this slide over here is to say, for a triangle, you calculate your area using one particular formula. And for a rectangle, you just use another formula. They cannot share the formula each other. Okay? But at the Polygon level, it's simply abstract. Okay, so now what we want to do is we want to minimize code duplicates. We want to make sure we can share stuff that can be shared and also have stuff in their own places when necessary. Okay, let's see the code quickly, and then we're going to trace it. Okay, so now, as I said, you have to know about the keyword abstract. So whenever you actually define a class, for example, Polygon over here is abstract. So that means you're going to have typically at least one method that will be abstract, which means at the runtime, somehow this method, this class over here, cannot be used as a dynamic type. But I will illustrate that point a little bit later. Okay. Okay. First of all, learn about the keyword abstract. Okay. Let's say we got, let's say use double rather than integer. Doesn't matter. Let's say we got an array of doubles as the sides for the polygon, and then we have constructor, which will take just an array of sides, right? And then we'll do grow. And for the grow over here, we simply increment each side by 1. Okay, that's also very easy. And notice that the way we grow the shape for triangle or for rectangle will be the same. So they can be shared. So that's why we're implementing the grow in the Polygon level. It's not abstract. Okay. And then similarly, when you talk about get parameter, also it can be shared. You can see we simply initialize that to be 0 and then simply add up, right, using the loop. That part, it can also be shared. We got the same formula for calculating parameter. Finally, you can see that's again something new. Because we got at least one method over here that's not implemented, so we'll simply declare that the class itself is abstract. And also the class over here is also abstract. also read the method. Do I have something to show you? Okay. So what we have got so far, okay, is this. We have an abstract class over here called Polygon, okay? So usually when you say it is abstract, that means at least one method that's abstract. And now in this case, it's exactly this particular method over here. Okay, notice that what do you have to do for this method? Nothing. All you do is declare the return type, which can be void, and also the name of the method, and whatever input parameters you might take, okay, and semicolon. So now abstract simply means declare signature only. No code, okay? Are we okay so far? Okay? Of course, in your actual exercise, it can be more than one abstract method if you wish, okay? But for now, just one. What you will see later is each of the subclasses, for example, rectangle over here and also triangle over here, they're going to share everything that's inherited from Polygon, but specifically because the gap area is abstract, so they have to implement it. That's what we will see. Okay, let's go over the code on the slides quickly, and then we'll go a little bit further. Okay, so get areas signature only. So now, Polygon cannot be used as a dynamic type. Let me illustrate this. What do I mean? Given this particular setup so far, okay, I'll show you on the Eclipse as well. Again, notice that this particular class is Polygon, is abstract. If I try the following line in my tester, I'll show you that in the Eclipse as well. If I say Polygon over here, P, is assigned to new Polygon. Okay? The question would be, would it compile? Okay? Let's think what you have learned so far without worrying about this particular example just yet. According to what we said before, this particular assignment will compile as long as the static type or the type that's being used on the right-hand side is a descendant class of the static type on the left-hand side, right? In this case, it is. So according to what we have learned, it should compile. However, there's something additional to it, okay? So that's something you have to be careful, okay? When you may have to consider either abstract class or later on interface into consideration, okay? So now for the left-hand side over here, we know that the static type is simply Polygon. So now the question is as follows. Can Polygon satisfy expectations on the static type Polygon? Can it? Well, think about what might be the expectations on polygons, right? If I declare P as of type Polygon statically, so that means I may call P.grow. This would be okay because I do have some code over here for me to execute. If I say P.get parameter, that's also fine. I also got code. Now, if I say P.get area, do you think that might be okay? No, because for this particular method here, it's simply not implemented. So that means any user trying to call P.get area in this case will actually crash. There's no code. So that's why it will not compile in the first place. Yes, question, anyone? Well, I already answered that. Okay, let me summarize what I'm trying to say here. When you actually have the right-hand side being the dynamic type, okay, here's a rule. The right-hand side over here, dynamic type that we're proposing cannot be abstract class, or we'll see later, interface. The same principle applies to both. The rationale is if we did allow that to compile, we might crash at the runtime. Because for abstract class and also for interface, they got at least one method that's not implemented. So if you call the unimplemented method, you're going to crash. Okay, that's the rationale. Okay, so guys, that's a very important concept to grasp. Okay, but now I want to show you something very quickly. Okay, I also made the source code available to you on the web, so you can also play with it. Okay, so now if you there are two projects you can import for the source code. I'll read it to you. One is called example abstract classes. Okay, let's just try the following. Okay, I will go into Polygon tester. Okay, there are certain comments in line that you can try. Okay, but one of the code I commented out already was this. you can see over here I declare polygon P. So static type of P is polygon, okay? And then, so this particular line I commented out because if I uncomment that, it's going to not compile. Let's see, okay? If I simply do that, okay, you can see there's a red underline over here, okay? Simply because polygon itself is abstract. So if you move your mouse over here, it would say, cannot instantiate the type polygon simply because it's abstract class, okay? So that's just one thing to show you, okay? I'll just comment it back. Guys, any questions up to now? Okay, so up to now we learned about abstract keyword, and also we learned about why abstract class cannot be dynamic type. Okay, two things. All right, let's go a little bit further on the slides, and you can try it out Eclipse as well, example code. Okay, so now let's talk about the subclasses for Polygon. The first one is called rectangle. And then you can see for here, we simply say rectangle. I'm going to trace the code together with you, so don't worry. Just give you some rough idea for now. Whenever you want to instantiate rectangle objects, you will pass the length, you pass the width. And then somehow you call super. What would super mean over here? Anybody? Yes. Yes, exactly. We're calling the constructor at the polygon. Exactly. Okay, we'll see exactly how that works. Okay. And then we simply, I'll explain this to you. Basically, you're going to make the first and third position to be the width, and the second and fourth position to be the height, the length. Okay, we'll see that. And then you can see that we inherit everything else was inherited. So you can think about we are inheriting basically the grow is inherited verbatim, and also get parameter is also inherited verbatim. The only thing that we have to implement is the abstract method. So that's why when you see rectangle over here, oh, sorry. If you see rectangle over here, the only method that we have to implement is this guy over here, right? That's the only one, okay? All other methods are inherited, okay? And very similar for triangle, very similar. So now, if you try the following substitution, you say polygon P is assigned to new rectangle 3, 4. That'll be okay. Because now rectangle is indeed a descendant class of polygon. Okay, so things work. Okay. Alrighty. So now triangle will be very similar. Okay, so we simply try to take the 3 sides. It does not have to be a right angle triangle. It can be any arbitrary triangle. So you got side 1, side 2, side 3. Of course, you may implement some exception handling to say the 2 sides, the sum must be larger than the third side. But let's not worry about it for now. Okay? And then you're going to call the constructor from the polygon again. I'm going to trace the code together with you. So don't worry for now. So now for the get area, so don't be too worried about. I'm simply applying the Heron's formula. So what I'm doing is I'll simply, first of all, calculate S, which will be the parameter, and then take the half. And then I'll simply apply S minus A, S minus the second side, and S minus the third side, and then take the square root. For the square root, I simply call math, the SQRT. Okay, that's basically the formula. Again, if you want to look up the formula, you can see it over here. Okay, it's this formula here. Okay, good. Again, okay, so now you can also have another substitution over here. Polygon P is assigned to new triangle. That'll be okay as well. Triangle is a descendant class of polygon, so that also works. Okay. So what we'll do now is we're going to trace some code together. Okay. Well, what I will do is I will move on to that one first. Okay. Before I go to the polygon collector. Let's have a look at this particular ones over here, okay? The basic one, okay? So what I will do is like this. Okay, just make sure it's big enough for you. Okay, good. Let's try one by one. Let's try with the first line. We simply declare polygon P over here. That's the first line. So polygon P is now declared, right? It might be substituted by any of the descendant classes polygon. Okay, that's not abstract. So let's see the first one. When we say over here, let's say P is assigned to new rectangle, 3, 4. So what we're doing over here is we're creating a new rectangle object over here. Okay? And then if we look at that, what I want to show you is remember this particular guy over here, right? That's the constructor for the polygon. That's the constructor. And now let me remind you very quickly. I'll trace this one together with you quickly. Okay. Okay. So now this is a constructor for rectangle over here, right? So now the first line there is a super new double 4. Okay. What that would do is thinking this way. So now when we try to execute this particular line over here, first of all, it's going to say super, which means polygon. Polygon, and then new double 4. It's going to be 4 because it's a polygon. Okay? So what that would do is it's going to create this particular size over here that is going to contain 1, 2, 3, and 4. Initially all 0. Okay, guys, this is what it will happen for the very first line over here. The super, new double 4. Are we okay with this? You can think about, in the case of triangle, you're just going to return just another array of different size. Okay, depending on the polygon you're talking about. We're just reusing the code. Okay, let's go a little bit further. Okay, if you go back to the slides over here, so now we're going to say slides at position 0 is assigned to length. So what do I mean by that? Okay, let me go back here. And then I'm saying over here, sides at position 0 is assigned to, so we got 2 arguments over here, right? The first one is the width, and the second one is the length. We're basically saying the side at position 0 is going to be 3, the width. And also the sides at position 1 is assigned to the length, and etc. So what that will end up having is 3, 4. We're going to have 3, 4, and then 3, and then 4. Make sense? Okay. Question, please. Oh, why is it 0 first? It's because if you look at, I'll show you this. Remember the very first line over here is calling super, which is a polygon constructor. And then we simply say new double 4. You can think about this as like an anonymous object, which will simply initialize a double array with size 4. And initially, nothing is assigned to the elements, so there will be... Oh, no, it's not null, because remember, double is a primitive type, so the default value should be 0, right? Of course, if we say person array, that will be null. It's double array. Okay? Guys, questions? Alternatively, if you really wish, you could have made just a double array with size 2, where you simply store just the width and length without any duplication. I'm just showing you one particular implementation. Okay? All right, that's about this. And the triangle will be something very similar. Okay, so for that one, I don't have to bother you. Okay, so after this, what we will do is, so now once we create this particular rectangle with 3, 4, 3, 4, okay, and then we're going to assign this new object's address to P. So now that means P is now going to point to this particular rectangle object, right? Again, we have polymorphism over here because on the right-hand side, as long as it's a descendant class of the static type of the left-hand side, which is polygon, we are fine. Okay? So now let's see exactly how dynamic binding is going to come into play. Okay? In this particular line over here, this line here, if I say p.get parameter, okay? So now, which version of get parameter am I calling? How many versions of get parameter do we have? There's only one version, which is defined in Polygon over here. So that means we're going to execute this particular fragment of code, okay, to run a loop, and that will add up 3, 4, 3, 4. Okay, that'll be 14. Okay, that one's easy. The next line is more interesting. When you say p.getArea, okay, if you think about it, when you say p.getArea, statically, p is polygon. For polygon, you can see itself has the getArea being abstract, but that's okay because execution depends on dynamic type. What's the dynamic type right now? Rectangle. Do we have a version for rectangle? Yes, we do. If you remind yourself over there, in the rectangle, we simply say getArea will be sides 0 and sides 1. Multiply them together. So what you will have is 0 and 1, so 3 times 4. Okay, so that's why you get 12 over here. So now what you want to see is over here, P instance of, and then if you say rectangle, would that be true? That'd be true, right? So we are basically asking, would the dynamic type of P, which is rectangle, satisfy all the expectation of rectangle? Yes. Okay, so that'd be true, just to remind you. So instance of is also something you want to review. Okay. Okay, so that'll be fine. So that'll be 12. So now let's do something very quickly to complete the story. Let's say we want to do another assignment over here. Okay, we say P is reassigned to this particular new triangle object. Okay, again, I wouldn't trace so many details, but I just want to show you something you want to review by yourself. You can see this is a constructor for triangle, right? Again, the super over here is going to create a double array of size 3. Makes sense because it's a triangle. So what you will get is you will simply get an array of size 3. And then because you're passing 3, 4, and 5, eventually it will just be 3, 4, and 5. Okay? So now, if you think about it, if I say P dot, oh, sorry, before I do this, and we are executing this particular substitution, which will be valid, because triangle is a descendant class of the static type polygon over here. Okay? So now P, rather than pointing to here, is now going to point to this object triangle here. And then when you say P dot get parameter, okay, again, we're calling this single version that's reused in the polygon, which is add out the sides. That'd be 3 plus 4 plus 5, you'll get 12. That one's easy. Okay? So now you want this line here is the most important. When you say P dot get area, which version are we calling? Triangle or rectangle? Depends on the dynamic type, right? Apparently you can see the diagram here. P is now pointing to triangle, so dynamic type should be triangle. Okay? So now I want to show you this. At this point over here, if you say P instance of, if I say rectangle, would that be true? At this point, no, right? Because it's pointing to a triangle. Triangle cannot satisfy the expectation for a rectangle. Okay, so that'll be false. On the other hand, if I say P instance of, and then I'll say triangle. That one there, because triangle over here, so that'll be okay. So that'll be true. Okay, so now if I say P dot get area is going to call, if you recall yourself, this hierarchy here, triangle class over here does define get area using Heron's formula. Okay, so just calculate this. Okay, if you apply the formula, what you get is 6.0. All you got to do is calculate a parameter, take the half, and then do that particular formula, apply. Okay, and then you'll get 6.0. Okay. All right, that's about making use of the polygon, with the 2 different dynamic types. It's very similar to you having students, and at the runtime you may have resident students versus non-resident students. Very similar. Okay. Guys, any questions for me up to this point? I hope so far no surprise, right? The only thing is about abstract you have to remember. Okay. Once we get to interface, you just have to make things even more extreme. So conceptually, it's not hard. Okay, you just have to know what the extension is. All right, so that's about this guy here. And now let's do a little bit more about polymorphic collection. Remember, we talked about an array of students, which is polymorphic, right? Because at runtime, each element in the array can be either resident students or non-resident students. We want to do the same thing. We declare something being an array of polygons. At runtime, it can be each element can either be a triangle or a rectangle. Okay, let's see how we can build it up. And we trace that a little bit quickly, okay, just to get some feel. Okay, let's see this guy over here. So what we'll get is polygon collector, okay? Okay, we got an array of polygons, and also we got a counter. Okay, not surprising, right? We have seen this pattern so many times. And then we say simply create, let's say up to 10 polygons we are storing. And then add polygon over here. And remember just last Friday, we talked about this, right? If I put polygon here being the static type for a parameter, that means I'm being very accommodating. Any arguments whose static type is a descendant class of polygon, which can be rectangle or triangle, it can be added. That's how we build the polymorphic array. Okay. And then you simply try to assign P to the corresponding position. Questions? Yes.
I think Polygon, because in the previous slide it says uses a dynamic type.
Which line are you referring to?
4.
Number 4. Let me see this.
Is it the same for the abstract class or is it not?
You know what? It's interesting over here. Oh, you know what? It's different. I see what you mean. It's a good point. Guys, I should have made this in the slides. The question was about line number 4, okay? It's different. Okay, let me explain that in isolation. Very good. Let me put on the iPad over here. When you say, what I said previously was, if you got polygon P is assigned to new polygon, if you simply do this, as we said before, this will not compile, right? Let's get it clear, okay? Because this is abstract class. On the other hand, when polygon is declared to be the static type for each element in the array, you can actually do it. But you're not, I'll tell you what, you're not really creating any polygon objects. Let me explain to you. Let's say over here, if I say polygon array, the difference is we got an array over here, okay? PS. It's assigned to new polygon 10. First of all, this is okay. The reason is we are not really trying to instantiate any polygon objects over here. We're just creating an array of size 10. And statically, it's simply just polygon. So what would this instantiate? What that would do is it simply say PS is now pointing to an array of size 10. So you got 0 over here, 1, all the way to 9. Each one of them is simply storing null. That's what it is doing. So you're not really creating any polygon objects conceptually. So that's why it's allowed. It's good pick. Okay, good. Okay. And what this will do is statically, each element over here is a polygon. But dynamically, it cannot be polygon, of course. It can be rectangle, it can be triangle. Okay, good. All right, and then add polygon here, just like I asked students as before. And then grow all. This one, I'm just trying to show you how you can write methods. So this one, I simply go through all the polygons that store, which can be rectangle or triangle. And then for each one of them, I simply want to grow. For example, you can think about this is what's happening here. Grow all. Conceptually, if you have a polygon collector like this, for example, dynamically, let's say if you have a rectangle and over here you have a triangle, let's say, there's a polygon collector. If I say PC.grow all, conceptually what I'm doing is I want to grow this to be bigger. And I also want to grow this to be bigger. That's what it is doing. Okay, the method. Okay, just increase the size for each polygon. Okay, so now, yeah, it's static type, and then dynamic type as well. Dynamically, each polygons at each position can be either rectangle or triangle, right? Okay, before I go to a second class that we want to talk about, I want to trace some code together with you, okay, just to strengthen the understanding. Polymorphic collection of polygons. Let's do that very quickly, okay? So what we will do is, let's do the following. So we have polygon collector, COL. Okay, COL is over here. It's polygon collector. And then we simply initialize that to be empty. Initially, NOP, number of polygons, simply 0. Every slot over here is pointing to null. Okay? And then let's try the following. Number 1, we'd say COL, the polygon collector. At polygon, statically, we are expecting a polygon. Right? So now any objects of type that's a descendants of polygon would be okay. So now we'll simply use anonymous object here, new rectangle. Would this be okay? Because it will be okay because rectangle is a descendant class of polygon. So that'd be okay. So what we are doing is we're creating rectangle over here, rectangle here. It'll be 3, 4. So 3, 4, and 3, 4. When we add it to the collector, what we'll do is NOP is now 0. So now 0 position should point to this particular rectangle, and then increment that to 1. Okay, pretty much the pattern we have learned about. Let's do the next one. So now when we say add polygon, again, new triangle 3, 4, 5, very similar, right? So now we are still trying to add into this particular collector. So we created this particular triangle here, 3, 4, and 5, as we explained in the previous example. And then NOP is currently 1. So we are trying to add to position 1. So now position 1 should point to this particular, it should now point to this particular triangle objects over here. After that, we should increment from 1 to 2. Okay, that's how the pattern works. So far, so good? Okay, so now it's pretty much similar exercise as before, but now rather than talking about just a single variable p, we're going to talk about different positions in the array. Okay? At this moment, I would like to have 2 tests for you. Okay? Before we get to these 4 lines, we'll get to them a little bit later. Okay, we'll get there. What I want to ask you about is this. If I say col dot polygons at position 1, for example, instance of polygon. Okay, I'm going to have 3 checks for you. Okay, give me one moment. Just saving some space over here. Okay, good. Okay, number 2 over here, I have this guy over here. And now I'm going to have, let's say, a rectangle. And finally, I'm going to have another one, triangle. Okay, and then I'm going to change this guy over here to be triangle. You can see basically I'm trying to do the same expression. Polygons at position 1. That's what I'm doing, right? I'm doing instance of. And the first one is polygon, second one rectangle, the third one triangle. Okay? Apparently each one of them is going to give me either true or false, right? And to really answer this question here, and also in your written test or in the exam, you have to be able to draw diagrams like that so you can see what a dynamic type is. Okay, let's start with the first one. Should that be true or false? True? The reason that should be true is because of this. When we talk about a position 1, we are talking about this particular position 1 is referring to triangle. Is triangle able to satisfy the expectation on polygon? Yes. What about rectangle? Can triangle satisfy expectation on rectangle? No, right? Can it satisfy triangle? Yes, that's exactly how you see. Okay, so eventually this will be true, this will be false, and this will be true. Okay, it's not really hard. You just got to trace the objects. Okay, some very easy exercise for you. So now we're generally going to see if you say collector 0, collector 1. So when you say collector 0, you're really talking about this particular rectangle. And when you talk about position 1, you're really talking about this particular triangle. Depends, right? So now when you call get parameter, you're going to get different result, apparently, right? So now what about you say position 0 that get parameter? You're basically getting parameter for this particular rectangle. So you add up these 4 numbers together, right? When you say this guy here at position 1 that get parameter, you're basically saying now this triangle add up these 3 numbers together. That's why you get different result. Okay, one more thing. The grow all over here. Okay, let me remind you very quickly about the grow all. The grow all is over here. So grow all is a method from Polygon collector. It's simply just going to go over all the polygons over here. So that would be this, this polygon here and this polygon over here. And then call the grow method on them. What does the grow method do on the at the polygon level? It will simply do, for the polygon, simply add out the sides by 1. Okay? You can think about eventually what you will have is this. Okay? The first iteration of this, we're going to modify at index 0. Index 0 is referring to this rectangle objects. We're going to increment each side by 1. So rather than 3, 4, 3, 4, it's going to be 4, 5, 4, 5. That's what you would do. So that means when you call the get parameter, it's going to give you a larger value. You can double check the math. Okay? And for the second iteration, I will be 1. In that case, you're basically talking about this particular triangle object and grow it. So that'll be rather than 3, 4, 5, it's going to be 4, 5, and 6. When you add it up, it's going to be 15. Okay? When you call the get parameter, of course. Okay? That's what's happening here. You can see we're just trying to do a very, very similar manipulation over here as we did previously, right? All the principles apply. Right? Any question about this? We okay? All right. Guys, are you sure? Okay. Well, good. Let's do one more example on this. So that'll be the polymorphic return value for Polygon. Okay. Okay, this guy here, we have seen that already, so I'm gonna, nothing has been skipped. Polygon tester, that's exactly what we just went over, okay? I'm not skipping anything, so that one is also fine. What I want to do now is Polygon constructor, okay? Let's see how the Polygon constructor should be defined. Let's have a look at that. Itself is very easy. First of all, we declare Polygon constructor here, and the constructor is simply just going to take an array of sides over here. Basically, if you give an array of size 3, that means you want to construct a triangle. If the input size is simply of size 4, that means you want to construct a rectangle. That's the intention. Okay, so we say, first of all, we say some polygon local variable p. If the input size over here, the length is 3, that means you want to do a triangle. You simply create, p should be substituted by a new triangle with all the sides over here, 3 sides. Else if the size, the length would be 4, that means we want to do a rectangle. In that case, we'll simply say p is assigned to a new rectangle. So now, I want you to pay attention to the 2 lines. Line number 4 and line number 8. Again, that's polymorphism, right? Because static type for p over here is polygon, as we declare in line number 3. Then dynamically, it can be either a triangle or it can be a rectangle. Depends. So we're going to trace some code to see this. Okay, let's assume it can either be 3 or 4. You can also implement some exception handling if you wish, but let's not worry for simplicity. Okay, so now, and also we got grow. Again, we just grow the geometric shape, the polygon. So now, again, you can see the line number 2 and line number 5, polymorphism that I just mentioned. Let's trace the code very quickly to get a feel. Okay, we're just going to see at the runtime how we can get different polygons. Okay, we'll see that. So what I will do is I'll go to the second tester, which will be polygon constructor. That's something I want to do. Okay, let me just go to iPad directly. So let's trace that together. Okay, so now let's try that. I put everything into context. Okay, to remind you, for the polygon constructor over here, we have an accessor over here called getPolygon. And then we're going to give an array of sides. That's what we're going to see. Okay? So now let's try that. Number 1, we're going to do polygon constructor. Let's create these objects. Okay? So what we will do is we're going to just create. So COM constructor is now pointing to a polygon constructor. Okay, just an object. Okay? And then we're going to initialize rectangle size, which is just going to be an array of size 4. So 3, 4, 3, 4. So now, let's have a look at this particular line over here. When we say P is assigned to polygon constructor over here dot get polygon, rectangle size. This one's interesting over here. Okay, let's pause a little bit here. Let's see exactly what we're doing here. Okay, let me help you understand the code here a little bit. CON over here was declared to be polygon constructor. Okay, and then get polygon is an accessor that we declare over here. What's the static type for this particular return expression? Polygon, right? So that means you can think about when you say con.getPolygon, the static type of the return value will simply be polygon. And now we are trying to assign polygon into P. Would that be valid? It would be, because P was declared. Actually, I kind of continue from the previous code. You can recall that we declare polygon P. That's what we did previously. Okay, when you see the example code, you will see. So now P was declared to be polygon initially. So now, can we assign polygon to polygon? Yes, we can. Okay. Let's see exactly how this line is going to be executed. That's really important to see. Okay. So now, rectangle size is 3, 4, 3, 4. Okay. So what I will do is I'm going to execute this particular accessor over here, and now the size will just be 3, 4, 3, 4. Is this if branch going to be hit? Not really, right? Because the size is not 3, it's 4. So what we'll do is we're going to say this will be true. And then we're going to say P is now assigned to a new rectangle with 3 and 4. You can see 3 and 4 over here. So what that will do is, at runtime, you can think about a P over here, eventually, is going to be assigned to a rectangle, eventually. And then we're going to get 3, 4, and 3, 4. That's what we'll get. Any question for me? So this one here is very similar to the getStudents method that we talked about last Friday. Again, let me summarize quickly, so just in case you get lost. Nothing's new. We're just declaring a method over here called getPolygon. The static type for the return value is simply just polygon. Okay? Dynamically, it could be a new rectangle, or it could be a new rectangle, depending on the size of the array you're passing. Right? In this case, we are passing a rectangle size, which is a size 4. That's why it's a rectangle. Okay? And later on, we're actually going to also try to do another construction. We'll do that. Okay? After this, let's do some exercise, do some checks quickly. Now, okay, can you tell me the instance of check over here? Actually, you already saw the answer, but let's check very quickly. So P over here, dynamically, is now pointing to a rectangle object. So now, is rectangle going to satisfy polygon expectation? Yes, that's right, that's true. The only thing that's false is about triangle. It cannot fulfill. Okay, that's false. And then when you calculate get parameter, get area, it will just be calling the corresponding version in the rectangle. So that one is also not hard. We did that already. Okay. And also, you can try to grow the polygon that's inside. Right. In that case, you will simply increment these sides to be 4, 5, and 4, 5. Okay, if you try to execute get parameter, get area again, it's going to be of different value. Okay. The final line I would like to emphasize is this line here. Let's say we initialize triangle size. So now it's an array of size 3, okay, over here. And then we say P is assigned to com.getPolygon triangle size. So now we are calling this triangles getPolygon accessor the second time. Okay, let's see that very quickly. So what we're doing over here is getPolygon over here triangle size is going to be 3, 4, 5. 3, 4, and 5. So what we're doing over here is calling this method for the second time. Okay, and then the size right now is 3, 4, and 5. So now apparently you can see for the first if statement, are we going to hit the if statements? We're going to hit that, right? Because now size.length will be 3. So that one's going to be true. So we're going to do this particular assignments. So that means we're going to create this particular triangle object over here with size 0, 1, and 2, which will be 3, 4, and 5. So we're creating this triangle 3, 4, and 5. And then when you go back to this code here, it's going to be assigned to this particular return value. So that means P, rather than pointing to over here, is now going to point to this triangle objects over here, right? All right. So now, if you do the instance of check, very similar, but now the dynamic type is different. So that means it will still be a polygon, that's okay. but it's not a rectangle anymore because it's not a, it's not a triangle anymore. It's not, okay, sorry, it's not a rectangle anymore. So that means it should be false, sorry. And then it's not a triangle, so that should be yes. Okay, good. You kind of get the idea. And then we call the get parameter, get area. It should all be called on this particular triangle objects. Okay? And then you can also grow the size, which you will become 4, 5, and 6, and call all parameter and get area again, right? You'll be similar result. That's the overall picture for the code, okay? What will be the best way to study about this example? Download the code and play with it. You'll be even better if you can run a debugger to see side by side, step by step. That'll be the best. I'll take a question in just one moment. Let me summarize about the abstract classes. Okay, that's it. Okay, that's something we just saw. Okay, what would be an abstract class? Basically, you got at least one method that has no implementation, at least one. Okay. So that means you're expecting the subclasses to implement those abstract methods, if any. Okay. And then you can declare the static type as an abstract class. You can say Polygon P, or you can say the parameter is Polygon, or you can say the return type is Polygon, which we have seen all the cases so far. Okay. And it cannot be a dynamic type because one of the method is simply has no code, so you cannot fulfill the expectation. Okay, so now you also have to see things like when I say Polygon P, and now if I want to get a polygon from certain sides, what should be the dynamic type? That's return. Okay, that's the example we just went through the last. Okay, that's about abstract class up to now. Any questions? Any parts you feel uncomfortable? Let me know. Okay. Fortunately, this is not covering the written test, right? Fortunately. But I think it's good to know, right? You'll be ridiculous if you claim that you know Java without knowing abstract classes, right? Or interface. But take some time to learn this. After the last class, we can still hold some review session for the exam. So in that case, you can still ask me. Okay. Okay, guys. Any immediate questions for me about abstract classes before we move on to interface? We're okay, right? Okay. So this is just one example for abstract classes, but for the lab. For lab number 7, you're going to do interfaces. Interface is very similar to an abstract class, very similar, except that we're going for extreme. You can think about in an interface, every method is abstract, which means none of the methods are implemented. All we declare in the interface will be signatures for the methods or headers. Okay? Let's see a problem to solve. Okay? Let's talk about point. Okay, we have seen points many times, in the course, but a slightly different perspective to it. How do we represent a point? What we have seen so far is simply store the x and y value. Okay. So now there is another way to represent the points. It's called a polar system. Have you ever heard about this before? Okay, let me just explain very quickly. It's not a math course, but just to really make the programming example work, let's talk about it quickly. Basically, we talk about two different ways to really represent your points. Okay, so now over here, there's something called Cartesian. There's something called polar. A user of your point class they don't care which one you're using. From their perspective, as long as they can know about the location for the points, then they'll be happy. How exactly you calculate the location is up to you as the implementer. Okay, but let's see the two differences. In a Cartesian system, you simply got x and y. That's very easy. Okay. What about the polar? For the polar over here, you store different stuff. In the case of Cartesian, you store x and y. So these are the two things you store. In the case of polar, you store two things. Number one, you store the distance between the origin and the point you're talking about. So that's a distance, r. And number two, you store the angle over here between this particular imaginary line and the x-axis over here. So we call that phi. Okay? So these are the only two values you store for the polar system. So now the question is, given r and phi, how do you calculate the location for the points? Well, you learned about trigonometry, right? Okay. Just for your information, if you want to know this particular side over here, it will be r multiplied by cosine phi. Okay. And this part will be r multiplied by sine phi. I assume you're okay with that. Okay. So now you can think about in the polar system, this guy here, the x value will just be r multiplied cosine phi. And then the y value over here will be r multiplied by sine phi. From the user's point of view, they have no idea whether you use this particular system over here or using this particular system here. They don't care. Okay? So this is a typical use case for interface, which means you want to support a certain set of functionality like get x and get y, but you have different ways to support them. Okay? Let's go over a little bit slides and we'll see the code. Interface is actually easier than abstract classes, I would say. Okay? Let's see. Okay, Cartesian system, also we got polar system, so a little bit more detail, you can refer to them, okay? If you really struggle with the math, yeah, you can ask me, that's fine. Oh, and by the way, you don't have to implement cosine and sine from scratch. You don't have to. The math class support all of them, okay? We're gonna see how to do that, okay? Okay, so now this is really important. As far as users of a point object is concerned, they only have to know how to do get x and get y. They just call these two methods, nothing else. Whether you use polar or Cartesian, they don't care. Okay? That's an important point. And then dynamically, either you're going to say get x by just returning the x value if you're using Cartesian, or it might return r times cosine phi in the polar system dynamically. Okay, we're going to see that. Let's see. So this is kind of the setup I'm going to do as an example. Okay. Let me come back to this particular example a little bit later. Actually, I can do that now, okay? Because the test case I'm going to run to you is like this. Don't worry, it's not complicated, right? I'll explain to you. Let's first of all, let's agree on sine 30 degrees will be 1 over 2, okay? Cosine 30 degree will be 1 over 2 multiplied by square root of 3. You can take it for granted, just for now, okay? The triangle we try to set up over here, so we can have the same points to be represented by either polar or Cartesian, is like this. Let's say we have this particular points. The distance is 2a, okay? And then the degree is 30 degree. So now we know that this part over here is going to be the distance multiplied by cosine 30 degree. And cosine 30 degree is 1 over 2. So that's why, cosine 30 degree is 1 over 2 multiplied by square root of 3. So if you do the math over here, it's now going to be a multiplied square root of 3, whatever a it is. So a over here can be 5, it can be 10, it can be 15. You can change the value for the tests, but you will see that, okay? And similarly, so now what about this distance over here? It's going to be 2a, the distance over here, times sine 30 degree, which we know is 1 over 2. So that's why you get a. So finally, the point that we are talking about is this point over here. For example, if a is simply equal to 5, in that case, we are talking about 5 multiplied by square root of 3 and also 5. This particular point can be represented by either the Cartesian or the polar. And we're going to make sure when the user call get x and get y, you're always going to get the same value, regardless of the dynamic type. Okay, that's what we'll see. But any question about the math over here? I hope that doesn't bother you too much. I hope. Okay, I assume you're okay. Okay, let's see a little bit code, and then we'll trace some code. How do we declare interface? Easy. Remember I said before, interface is basically like an abstract class where every method is abstract. Since it goes for so extreme, you don't even bother to mention abstract for the methods anymore because every method is abstract. Okay? So now if you look at the interface over here, this is the second keyword you have to know for today. Okay? You only had to learn about interface. This is another keyword you have to learn. Well, I'll mention that. So you will say interface points, and then every method in the interface will just be declared with their signature, get x and get y. So that means no implementation just yet has been supplied at this level over here. So what will be the consequence of that? Can you say point P is assigned to new point P? Oh, sorry. Can you say the following? Let me make it absolutely clear. Can you say something like point P is assigned to new point? You cannot, okay? Because this is interface. Everything is abstract, so it cannot fulfill the expectation. On the other hand, what you can put eventually is you can say new, maybe Cartesian points. Or you can say new polar points. Either one of them is okay, because both of them are descendant classes that we're going to create. Okay, good. Conceptually, that's not hard. Okay, so now, so the interface simply declare a user of the point. They will simply call get x and get y. They don't have to worry about which system is being used under the hood. Okay, so can that be dynamic type? So now let's have a quick look of the implementation, and then we'll trace it. Okay, so you say Cartesian points. So now the second keyword you have to know. When you actually got abstract class like a polygon, you say rectangle extends polygon. But when you have interface, you don't say extends, I'm afraid. You have to say implements. So watch that when you do the lab. Okay, you're going to say Cartesian points implements the points. And then for Cartesian system, we simply store x and y. Easy, just like before. So this one should be no surprise to you. And then we simply initialize the point using x and y, and also get x just return x, get y just return y. Okay, no surprise over here. Okay, and of course, Cartesian point implements all the abstract methods from the interface, so we can use it as a dynamic type. Okay, that's not an issue. For your curiosity, let's see how the polar points will be implemented. It's actually quite straightforward. You just have to call the relevant methods from the math class. That's what you would do. Okay, polar points implements point. Again, you don't say extend, you say implements. And then you would say phi, the angle, r, the distance, right? So now when you first initialize the polar point object, you will pass the r and also the phi. Oh, by the way, just for your information, mathematically, when you pass the angle, it must be specified in terms of radians. Okay, but you do have conversion of radians in math class. I'll show you. Okay, so it's not, should not be a block to you. And then what we will do is we'll say get x. So now you say cosine multiply r, right? As we said before, you can simply use a cosine method, a static method from the math class. Okay, that one is not hard. And then you can say return for the get y, return math.sine phi multiply r. Okay, everything we have done so far simply correspond to this initial illustration over here, right? We just got two possible ways to support get x and get y. Okay, which one the user chooses doesn't really matter. The output the external behavior should be the same. Okay, let's now trace a little bit code together with you. Okay, so what I will do is I'll switch to iPad over here. Let's do that quickly. Okay, let me just remind you, we got a point over here, which is interface. And then we got Cartesian points, which implements points. We got polar points, which also implements the points. And then over here, in one case, we store x and y. The other case, we store phi and r. Okay, so now only a few lines to chase over here. Let's do that quickly. Okay, let's do the first one. Here, we simply set up. Oh, remember the diagram I talked about, 2a, etc., right? I'm just using that. So now I'm simply saying a will just be 5. So that means 2a will now be 10. Okay? So now over here, a multiplied by this, that'll be 5 multiply square root of 3. And over here, it will be a, which will be 5. So that means we are talking about this particular point, which is 5 multiply square root of 3 and also 5. Okay? That's the point example we are doing. Okay, so what we'll do is set this up, and now we say point P. We simply declared P statically to be points, interface type. So point P is here. Okay, let's now do line by line. Okay, let's do the first line. If I say P is assigned to new Cartesian points, First of all, this should compile because Cartesian points over here definitely can satisfy all the expectation for static type of P, which is point, get X and get Y. We have implemented that already. So now, what's going to happen when we do this? Okay, what's going to happen is over here, because you pass X and Y, okay, let me just substitute here. X would just be 5 multiplied by square root of 3, and Y would be 5, right? Just starting just from here, okay? So now, this is 5 square root of 3, and this is 5. So what I'm doing over here is creating this Cartesian point objects. And then X would be 5 square root of 3, and this would be 5. And then I'm going to let P assign to it, polymorphism. So now if you say P instance of polar points, would that be true or false? False, right? Okay, just double check. Okay, good. So now if I say the next line, which is important, if I say P dot get X and P dot get Y, what would that be? Well, P dot get X will be calling get X, return X, just return this value over here, right? When I say P dot get Y, so it's going to say return Y, right? And I'll just return 5. Okay, that's easy. It's simply going to return this value and this value. Okay. The interesting bit is the second one. Let's see the second one. The second one over here, let's see this. P is now reassigned to polar points. Okay? What that would do is like this. First of all, we'll simply pass 2a. 2a is like the distance over here, right? It's simply just 10. That's the distance, right? It's the distance between the points we're talking about and the origin. Okay, that's what we do. That's R. And also, the angle we're going to do, 30 degree, as we said before, but now the formula requires to actually convert to radians. Okay? In the math class, there is a method called 2 radians, so that's okay. You simply call that under 30. Okay? But conceptually, you're going to put 10 over here for the R, the distance, and 5 will just be 30 degrees. Okay, I'll just put it conceptually. And after that, we're going to do the substitution. So now P, rather than pointing to here, is now going to point to this particular polar points, right? So now, if you look at that over here, when you say P dot get X and P dot get Y, I really want you to pay attention to this. Previously, when we say P dot get X and P dot get Y, we are basically calling get X and get Y dynamically from Cartesian points because Cartesian point is dynamic type. But now, since we changed the dynamic type already, when we say get X and get Y, are we going to call different versions? We are. We're going to call get X and get Y from exactly over here. Okay? So that one is also going to return the same value. So from the external user's point of view, it's just going to be the same. Okay? Let me just show you some experiment very quickly. So that's why you can play with the example. Okay? I'll show you. When you download the source code from the Eclipse, okay? So that's in a different package. So if you go into example interfaces, okay? There's a project there. And then go to the point tester, okay? You will see exactly what we have set up the things, okay? I'll show you quickly in the code. So we declare point P over here, and also we set up the particular triangle that we talk about, okay? And then we simply say from line number 15, dynamic type should be Cartesian points, okay? And then we try to print out X and Y, okay? You can see we say P dot get X and also P dot get Y, okay? Now in line number 22, we try to create a new polar points, right? And then we try to print out 30 and 31, P dot get X and P dot get Y. So now from the external user's point of view, they should see exactly the same value. They should, right? That's the value about interface, because regardless of the dynamic implementation, external behavior should be the same. Let's try that. If you execute it, you're just going to see, you can see here, Cartesian is going to be 8.66 and 5.00, okay? Versus the polar is going to give you just the same value, even though computational-wise, they're using different versions of get X and get Y, right? So that's about the interface. Okay, so now the interface, as I said before, is simply go extreme. All the methods there are abstract. So that's why you don't even bother to mention abstract, because every one of them is abstract. And then, okay, so the idea is every class that implements the interface has their freedom to really implement every method, like in your lab number 7. Okay, you will see that. Okay, so now watch, just similar to the case for abstract class. The interface may be used as the type, statically, the static type. It can be for parameter type, or it can be for return type, right? The same idea for polymorphism. Okay, so now, of course, you cannot use interface as the dynamic type, okay, as before. Okay, finally, it's the final slides. The best I could do in the lecture is to give you the typical example for abstract class and also interface. But let me give you a little bit more principle, okay, to really design. Beyond this course, whether to use interface or to use abstract class depends on what you need. Okay, let's see some guiding principle. Okay. Use the interface when you have certain common set of functionality you want to support, but you have different ways to support them. For example, get X and get Y. You want to support get X and get Y. However, how to support them depends on the strategy you choose. You might choose polar, you might choose Cartesian, which is quite different. Okay, but from the external user's point of view, it doesn't matter. Okay. Okay, so that's why you have an interface called point and get X and get Y, right? And then you might do Cartesian point versus polar points, right? That's the interface. In your lab number 7, I think it's something called dictionary, right? It's either using one array or using 2 arrays, okay? Just 2 different strategies. But what's their goal? To support the dictionary operations, okay? That's something you can link to the lecture, okay? When you do lab number 7. What about abstract classes? I would say abstract class is a little bit like a more mild version of interface. You only choose one or more methods, not really all of them. Only one or more methods to be abstract, in which case you still have some code reuse into the subclasses, like a grow or like the get parameter. But the get area, for example, is abstract, so they have to be implemented in the subclasses, right? Okay, so only some, not all. Okay, that's kind of the principle. So if you find that all the methods should be abstract, go for interface. If you find that only certain methods should be abstract, are implementable, that should be abstract classes. That's a very rough guideline. Okay, of course, you got to go build some experience on this. Okay, let's say abstract class Polygon. We actually got get parameter. That's common. So that's something we can already implement in the Polygon class. So that's why it should not be an interface. We do have some implementation that can be shared among the subclasses. And then you can declare get area, and that one there must be abstract. You just don't know how to implement that at the Polygon level. Okay. All right. We are kind of like 3 minutes ahead of schedule. Okay. Any questions for me? Okay, let me give you a concluding remarks over here. So this lecture over here about abstract classes and interfaces is only a slight extension to what you have learned about inheritance. Okay. So all you have to watch for is the abstract keyword, and also abstract keyword, also interface and implements. And then to go through the example that we did about polymorphism and dynamic binding. And also the final slide is some guiding principle you can refer to beyond this course. Good. Okay, I'll see you this afternoon for the review session.